Hey guys, it's Miss Stratton, and I have our first set of motion notes. The first thing you'll notice is a link to a YouTube video. It's only 1 minute. It's a quick scene from the movie Despicable Me where we meet a villain named Vector, and that's because we'll be talking about vectors this unit. So if you want to give that a watch really quick, that might be enjoyable for you. Okay, so as you may have seen in that scene, Vector is the villain Vector, named himself that because he's saying he has both magnitude and direction, right? Direction meaning he knows where he's going, and magnitude meaning like strength or the kind of the numerical portion of a vector. So he also mentions that these are often drawn as arrows. So with an arrow, we're going to see, shorter arrows mean less magnitude, longer arrows mean more magnitude. And of course, with an arrow, we know its direction based on where it's pointing. When we have more than one vector, we have what's called a resultant vector. So that's referred to as the vector sum of two or more vectors, even though we'll see it's not necessarily always adding vectors together necessarily to determine the resultant vector. So our to describe motion, we need what's called a frame of reference. So that's just a system or group of objects that are not moving with respect to one another, or they're not moving compared to one another. So as I sit here, I have like the floor under my chair, me, my desk, my whiteboard behind me. So those objects are not moving compared to one another, but of course we know that technically they are moving since the Earth is rotating and also revolving around the sun. So frame of reference just gives us an idea of like what we're comparing our motion to. So like as I sit here, I would say that, I am motionless or I am stationary compared to like the objects in my classroom. But of course, on a bigger scale, I am technically moving. So frame of reference is important to consider when we're talking about motion. And then, of course, the motion of those objects is all relative. It just depends on, again, what frame of reference we are referring to. So in our first picture, we've got two people. The person that's on the ground is saying, wait, hold still. And the person that is on the box car, which we can assume is moving since this person is saying, wait, this person on the train is saying, I am standing still because they are still compared to the train car, but they are not still compared to the ground or the person who is on the ground. So it's all about what you're comparing your motion to. In this picture, we have some individuals also on train cars, and we also see some arrows or some vectors. So they're showing the direction of our arrows. So in this case, they're both in the same direction. In this case, they're in opposite directions. And those arrows are also indicating the magnitude of the motion. So we can see like the 1 meter per second arrow here is shorter than the 6 meter per second arrow because 1 is less than 6. However, if I was making this diagram, for example, I probably would have made the 1 meter per second a little bit smaller since this 1 meter per second and 4 meter per second arrow look pretty similar. So technically we would want to draw that 1 meter per second one a little bit smaller. So let's talk about this. So we haven't yet talked about velocity, but the idea is that we're looking at the direction we're going and how fast we're going. So this person isn't just still on the train car like this person was over here. This person is walking. They're walking forward, and the train happens to be moving in that same direction. So if we wanted to talk about how fast this person is moving compared to the ground, or our frame of reference, our stationary a stationary object, we have we would add these together since they're in the same direction. So 1 meter per second plus 6 meters per second would tell us that this person's moving at 7 meters per second compared to the ground. This person, on the other hand, is walking toward the back of the train or in the opposite direction. So since these are in opposite directions, we're going to subtract them. So our person, compared to the ground, it would be moving at 3 meters per second, still to the right, even though they're trying to walk toward the left, because we can see that obviously this is has a larger magnitude than 1 meter per second does. So compared to the car, each person is walking at 1 meter per second, but compared to the ground, person A is walking at 7 meters per second and person B is at 3 meters per second. So again, that vector sum isn't necessarily always adding because it depends on the direction of our vectors. Okay, so the next things we use to describe motion, we talk about the distance that an object has traveled versus the displacement of that object. So distance is just the length between 2 points, and it's going to be the entire journey of our object. So this picture, for example, shows that maybe someone is walking and they walk up here and then down here and then up here and then back down here and then they end here. Displacement is only from the starting point to the ending point. It also includes a direction with it. So that means it's a vector, right? Vectors have magnitude and direction. So we can see where displacement is labeled here. It's an arrow, right? It's a vector showing the direction that this person traveled from beginning to end. So another example is someone maybe walking to school. So they probably are going to stay on the city block. So they go 1 block, 2 blocks, 3 blocks to school. That would be their distance because that was their entire journey. But their displacement would only be from the starting point to the ending point. And so that's basically if you were, flying overhead, you could go directly from starting point to ending point. That's our displacement. So we'd say 5 blocks northeast, for example, for the displacement here. For these objects, again, displacement is just starting point to ending point. So for object A and for object B, they only moved in one direction. So we just count, how many spaces they moved. So object A, I guess we'll go from the or where the arrowhead kind of starts. So it went 6 spaces. For B, it went from 12 to 8, so 4 spaces. And then we can see for C and D, the object moved a certain amount, but then it came back and then it came forward. So again, if I wanted to calculate the distance, I would add all of those together. But if I want the displacement, I just want from the starting point, so 2, to the ending point, which appears to be kind of in the middle here at like a 9, so 7 total, even though really it went from 2 to 10, so that's 8, plus another 2, plus another 1. So distance is the whole journey. Displacement is just starting point to ending point. All right, guys, thanks for listening. That's it for now.